All right, this is the last section of new material in Chapter 2, and it's called the Mean Value Theorem. So to start with, we're actually going to encounter a theorem that's not called the Mean Value Theorem. This is Raleigh's theorem, and Raleigh's theorem says the following. Suppose that f is continuous on the closed interval ab, and differentiable means you can find a derivative on the interval, the open interval ab, and that f of a equals f of b. Then there is a number between a and b, called c, where f prime of c is 0. So fill in those details, and then I'm going to draw you a picture, and you're going to be like, well, yeah, of course there is. That's what you're going to look at, so you're going to say when you see the pictures. All right, so in layman's terms, continuous means we can draw it without picking up our pencil. Differentiable means it's smooth, no cusps like Dr. Bond was talking about, where it had that sharp turn on that absolute value graph. We don't have anything like that going on. So we've got a nice function. I mean, it's behaving well. The extra condition that we have is that the f of a and f of b are the same. That just means the y values at a and the y value at b are the same. So whatever they are, they're at the same height. So something like this is going on at the endpoints. Okay, they're the same endpoint. So this is f of a, and it equals f of b at this location. So no matter how we connect a and b together, there will be some place between a and b where it has a slope of 0. So imagine that it looked something like this, right? So clearly there is a location roughly right here between the value of a and b. So here's my c that this is referencing. And at that location, my tangent line is horizontal. And this just guarantees this, that there's one point that does this, but there certainly could be more than one point like this too, depending on how the graph is connected. It could be, again, over here, here's my f of a and my f of b. It could be that it's connected like this, right? Where it's got two locations where it actually has this property. We aren't guaranteed that it's going to have two, but it certainly could have more than one. So like this would be like C sub 1, for instance, and we'll call this one C sub 2. There's two spaces where they have these horizontal tangent lines. And even if you didn't want to think that it had this nice sort of curving feature, it could flat out just be a horizontal line itself already. And if it had a horizontal line, its slope would be 0 everywhere, right? I mean, like that would be a legitimate way to connect them that wasn't what I've already drawn, sort of looks a little bit more like a polynomial kind of graph. Okay, so this is called it's called Raleigh's theorem, and it's sort of a precursor to the mean value theorem. So let's talk about what the mean value theorem is, how it's different than this one. The mean value theorem says that suppose that f is continuous on this interval from a to b, closed interval, and it's differentiable on the interval a to b, so the conditions are the same at the beginning, right? Same conditions. Then there exists a value c between a and b, such that f prime of c equals f of b minus f of a over b minus a. So fill in those details, and then we'll talk about how this is different and how it's the same as the last theorem. The first question I want to ask you is, what is conspicuously missing in this theorem that we had in the last theorem? There's a condition that's been missing, or that is missing. Right. This says that there's no condition here that f of a equals f of b. So that's just not here. Now, certainly if f of a equals f of b, then the numerator on this fraction right here would be 0 and then we have the b minus a, so we get 0. And then, so if f of a equals f of b, this actually still becomes the same theorem we already had. I have a c between a and b such that the derivative is 0. I mean, so this is just sort of a bigger picture than what Raleigh's theorem is. Raleigh's theorem is just one specific situation of the mean value theorem. So let me talk in picture form about when what the case looks like when f of b and f of a are not the same. Because that's where these are actually different, is what happens if the endpoints really don't match. So we're going to take a picture, and I'm going to draw a graph where they actually do not have the same endpoint. So here's A, here's B, and I'll draw it like this. Oh, hang on. So if I've drawn that something like this, here's f of A, and up here roughly is f of B. They're not at the same height. So what in the world is this formula right here? You've seen this before, not written quite like this, but you've seen it before. What is that formula? Do you have it, Edgar? It's slope. All this is slope, right? I've got two y values subtracted on top, the same two x values where those y values are evaluated on bottom. This is just equation for slope. So this is saying that if I take those two red dots right now and I connect them with a line, I could find the slope of that line. All right, so there's my line connecting f of a, or connecting the point at A and the point at B together, and we could find the slope of that line. Okay? All this theorem is telling us that there is a location between A and B. Okay, so somewhere on the curve up here, there's going to be a location where the tangent line has that same slope. Okay, so now my picture's not going to be perfect, but it should be at least fairly convincing that this point right here seems a reasonable point, maybe even a little bit further to the right. Seems a reasonable point that if I drew the tangent line here, that's not a good one, that those two that tangent line and the secant line that I drew before are actually parallel. Okay, and if that's the location, then that's the point that they're referencing and they're calling it C. And there's nothing about having to be halfway in between or anything like that. Mine kind of looks like it was halfway in between, but that's just by chance. Okay, so this is the mean value theorem. It says that this will always happen. Now imagine the last picture that we had over here. I'm going to go back a slide. If we had the condition right here and we tried to do the same thing and we connected f of A and f of B together, we'd have a horizontal line, right? And then we'd have this tangent line that we already drew right in there. So it would be exactly what I've said. It's just a very specific case where we have this derivative specifically being 0 instead of being just in general any slope. Okay? Now, a few things here to notice, and I'll use this theorem just because I'm here already, is that there are some conditions for this to be true. First, it has to be continuous. So if you got something that's not continuous, we're sort of up a creek. It may not work. It has to be differentiable. Again, up a creek if we don't have that condition. And then on Raleigh's theorem, we have to have the condition that the endpoints match. On mean value theorem, we don't. So anytime we are working with this theorem or trying to apply these theorems, we have to make sure that we have the conditions that actually work to apply these theorems. Okay? So let's take a look at an example. The directions say to check the hypothesis, that's what I was just referring to, those conditions of Raleigh's theorem and or the mean value theorem, and then to find the value of C that makes the appropriate conclusion true, and then illustrate with a graph. So the first thing we have to check is we have to check the conditions. So the first condition is that it has to be continuous. The second condition is it has to be differentiable. And the third condition that we're going to check is we're going to sort of ask ourselves, does f of b equal, or does f of a equal f of b? So we're checking these three conditions. If the last condition is the only one that fails, that's fine. It just means that we're in the mean value theorem case instead of Raleigh's theorem. Okay? So we have to check these conditions, and we have to be able to justify yes it is or no it isn't with a little bit more than just like check mark, yeah I checked it, you know, a reason for doing so. So this graph is the graph of f of x equals x squared plus 1. Is it continuous? Yes. How do you know? Because it's a polynomial. We had a theorem back in chapter 1 about talking about polynomials. It's a polynomial, it's continuous. How about the second one? Is it differentiable? Yes. How come? You can take a derivative. That's true. But actually, it's a polynomial also. I mean, it's a differentiable also because it's a polynomial. We had a condition as well talking about when graphs were differentiable. And polynomials are differentiable everywhere. So the answer to both of those questions is yes. So we do, in fact, have one of the two theorems happening. How do we test result number C, or 3 here? What do I have to do? Right, so I'm going to find what is f of negative 2 and what is f of positive 2, because this is the interval I'm being given right here, right? So what is f of negative 2? 5. And what is f of 2? 5, and these are, oh my goodness, equal, right? So since these are equal, what does that mean for us? Yeah, we have the first one. I mean, we have the mean value theorem, but more specifically, we have Raleigh's theorem here, right? So all of this tells us that we have Raleigh's theorem. So Raleigh's theorem applies. So now let's go back to Raleigh's theorem and look carefully at what it means then to have all those conditions happen. Okay, over here, we've satisfied all the conditions, which means we are to this point right here, my red line. If we have those conditions, then there is a number between our two endpoints, so in our case between negative 2 and positive 2, where the derivative equals 0. Okay? We know that's going to happen according to Raleigh's theorem. Now, using the calculus that you know so far, we're going to actually find the value of C. So how do we do that? So we know there has to be a location where f prime of x is equal to 0, according to Raleigh's theorem. How do I find f prime of x? Yeah, I take the derivative, right? Y'all know. You know how to find this derivative. All right, so what is f prime of x for this function? It is 2x. And where in the world does this equal 0? This happens at x equals 0. So this right here is my C, yeah, we'll do it that way, is my C value that I'm looking for. Okay. Thus, let me write it differently. There exists C, which is 0. And it's between A and B, right? So between the negative 2 and positive 2, where f prime of C is the value, right? F prime of C, or f prime of 0 in our case, is actually equal to 0. That's what we found out. And we found the location. We found out that C value that we're looking for in this particular example is the value 0. The other condition, or the other piece of that direction said to illustrate the conclusion with a graph. So we're going to draw a graph of this function. What does this function look like? Yeah, it's a parabola. What can you tell me about the vertex of the parabola? Okay, it's opening upward, that's true. Where is the lowest point, the vertex, going to be? Yeah, it's 0, 1. So it's along the y-axis. Right here, and then it's opening upwards, you guys are saying. So does that look like a fair graph for this? And it's supposed to go out here to negative 2 and to positive 2. And if I've drawn them well, and I'm not going to guarantee I have, but it's not too bad, they should be the same height of 5 here, right? So to illustrate this with the graph means that I should be able to draw a tangent line at the C value I just found, which was 0, x equals 0, and the tangent line should be horizontal. And is it? Yeah, it is. Let me draw that in there next. So it looks something like that. So this is what it means to illustrate this diagram with a picture. Okay, this is the illustration we're looking for, the graph that shows that horizontal tangent line, and that it's occurring at the C value that is between the x values of my interval, of the endpoints of my interval. Okay, we're going to do another example, a little bit trickier in terms of the equation. All the same directions, okay? Illustrate the graph and check the hypothesis, all the same directions. But our equation is actually f of x equals sine of x. And this is going to go between the values of 0 and pi halves. So what do I have to check first? What's the first thing to check? If it's continuous. Okay, so somebody else tell me the second thing we're going to check. Differentiable, good. And someone else who hasn't said anything yet, tell me what the third thing is to check. Right, f of a equals f of b. And I actually have a and b, so I'll go ahead and write in here. We want to check that f of 0 equals f of pi halves, right? So these are my 3 questions. So to start with, continuous. Yes, how do you know? It's a sinusoidal curve. You're right, because it's a sine curve. And it's another one that back in chapter 1 we had a theorem that said that when you have a sine curve, it's continuous everywhere. How about the second condition, differentiable? Yes, why? Because it's a sine curve. Again, we had a theorem that said sine curves are differentiable everywhere. They're smooth, right? Last condition, f of 0 equals f of pi halves. Well, we have to test that, right? So what is f of 0? Well, it's sine of 0. And what is f of pi halves? Well, that's sine of pi halves. So what is sine of 0? Good try. It's 0, yeah. Sine of pi halves? That's 1. So what are we going to have to say about this one? Yeah, these are not equal. So this one's a no. They're not equal. So since the answer is no, what does that mean? Yeah, we're going to use the second one. So the mean value theorem, I'm going to abbreviate MVT. Almost looks like MVP, but it's not. MVT. MVT applies. Basically, since the f of 0 does not equal f of pi halves. That's what that means. Or that's why that's happening. Okay, so what do we do next? What's our next step? Yeah, we're going to actually see if we can find a location where something happens. Now we're going to need a derivative. Let's go back actually and look at these directions over here. I need a derivative. That's the left-hand side of this equation. What else do I also need? Yeah, I am going to have to calculate slope with the actual equation itself. So I'm going to calculate 2 things on this particular one. Mean value theorem, I calculate 2 quantities. Calculate the derivative, and I calculate the slope. All right, so that's where I am. Let's do the derivative one first, because you guys mentioned that one first. What is f prime of x for this equation? Good, cosine of x. And we want to know where this is equal to something, but it's not 0. We're not looking for this equal to 0 because that's Raleigh's theorem. Okay? So I need to fill in the what's it supposed to equal. Well, I don't know yet because I haven't found the other side of the equation. Okay? So in fact, let me just pause for a moment and we'll actually find the other side of the equation. So I also need to find f of b minus f of a over b minus a. I need to find the slope. So my 2 values are at pi halves and at 0. So I want f of pi halves minus f of 0 over pi halves minus 0. F of pi halves, I already found it. On my previous slide, it was 1. And f of 0 I already found on my previous slide. It was 0. So if you're struggling to remember, that's actually what we tested over here. Right? We plugged in 0, we plugged in pi halves, and we got the values of 1 and 0. All right, so over here, this is then going to be over the denominator what? Pi over 2. So this is a little awkward looking. It says 1 over pi halves. How could I simplify that expression? 2 over pi. So this is just multiplying by the reciprocal, right? So I could multiply by 2 over pi so that I can eliminate the double fraction going on, the complex fraction. So what my mean value theorem says, it says that the derivative should equal the slope from over here. Okay, the derivative we found was cosine of x. And the slope we found was 2 over pi. Everybody good so far? Okay. Now you're going to have to put your trig hats on. I'm not supposed to find out what is cosine of x. I'm supposed to find out what is x. How do I do that? Yeah, inverse cosine. Some of you are saying what the notation looks like. The notation looks like a little -1 up here, right? Now, in your calculator, that's how we're going to do this, because obviously 2 over pi is not a measurement that we have on a unit circle or anything like that. So grab your calculator. Please make sure you're in radian mode. That's very important. Be in radians. Okay? You're going to need to be in radians for the rest of the semester, so you don't need to change that. Radian mode. And you can get the inverse cosine button usually by hitting the second key and then the cosine key. And that puts the little negative up there. Okay? Inverse cosine of 2 over pi. What do you get for this value?
0, 7.
Okay, 4 decimal places is what our book usually likes, so that sounds good. Is everybody getting that kind of value? Excellent. Okay, so this is actually what we have. I mean, so, and just as a reference point is to remember, our interval, they actually will call this C. So C equals 0.8807 is on the interval from 0 to pi halves. Roughly, what is pi over 2? Do you know? Right, 1.57 is good enough. I just want you to see for sure that that 0.88 really is between those values. You guys see that, right? I mean, it really is between those values. So it's on the interval, and gives us a, you know what, let me say it this way. It has a tangent line with slope 2 over pi. Mean value theorem said we were going to have this happen, and we in fact verified just right now that it did in fact happen. Now we need to do what? There's one more thing to do. What did the directions tell us? Do a graph. It said to illustrate this with a graph, so I need to draw a graph of what's going on here. This graph is the graph of sine. I suspect you know what the graph of sine looks like. We don't need the whole graph of sine, though. How much of the graph do we need? Yeah, not even a whole period, actually. Yeah, just 0 to pi over 2. And so there's 0, we'll say there, and let's say that this first hash mark is pi over 2. Should have left myself a little more space at the bottom. I'm sorry about that. Graph of sine should be at 0, that is at the origin right here, right? And it should be at 1 right here. Right, so this is not a full period at all, right? This is just this tiny little bit of the graph. And on this portion of the graph, it looks something like that. Now imagine, and you're going to do it yourself, don't even just imagine, actually do it. I want you to draw the line that connects those two endpoints together. So draw the secant line. So my secant line looks something like this. Okay? And then your C value, and it's a bit of an eyeballing for the picture. You're doing a sketch here. This is not an accurate drawing. But the C value is the location between 0 and pi over 2 that has this same slope for its tangent line, right? So roughly, maybe around right here. Move it over just a little bit. There we go. And again, if I draw the tangent line then, okay. If I've drawn it well, these two lines should be parallel. All right? It should really look like a tangent line. Mine looks not quite right. But you have the right idea. This would be the location C here that is between 0 and pi over 2. This is the picture that they're referring to. Any questions on that one? All right, let's take a look at another theorem. Theorem 8.2 says the following. If f is continuous on the interval and differentiable on the interval, that sounds a lot like what we've already been working with, right? And f of x equals 0 has two solutions in AB. So this piece right here f of x equals 0 means that we've got a y-intercept, right? I'm sorry, an x-intercept. The y value is 0. So we're crossing the x-axis, in other words. So we're crossing the x-axis twice. Then f prime of x equals 0 has at least one solution in AB. And again, this right here is talking about slope. The slope is 0. So this just begs for a picture, just like the other ones have. So if we have a graph that crosses the x-axis at least twice, so here's a graph crossing it exactly twice for my picture. So here's A, and we'll call this one B here. Then there's at least one location between A and B where I have a horizontal tangent line. Well, yes, of course there is, right? There's no way I could have drawn this and that not happen if I've got a continuous and differentiable function. So on this graph right here, you're looking at this point right up here, something like that, right? So this is the location where we're referring to. Now, there's nothing that says that it just has to cross the x-axis only twice. It could cross the x-axis more than that. So that's what the next theorem is saying. The next theorem says for an integer n greater than 0, f is continuous and differentiable. Get used to those phrases. They're in all of them, right? Continuous and differentiable. And f of x equals 0 has n solutions. Okay, so not just 2, but maybe 3 or 4 or 5 or 10. Then f prime of x equals 0 has at least n minus 1 solutions. So in other words, if I had 5 x-intercepts, then I would have 4 locations where I had slopes of 0. If I had 10 x-intercepts, I'd have 9 places where the horizontal tangent line was happening in my graph, between the endpoints that we're referencing, within whatever interval we're looking at. So this can go right, in terms of your notes that you're taking, this can kind of go in the space above, right beside the other picture. I'll draw one more of these. And I'm just going to draw one with, I'm not going to draw it with 10 intercepts, but I'll draw one with 3 intercepts so you can kind of get a picture of what's happening. So if we've intercepted here at A, and at B, and at C, because the graph does something like this. So there's my 3 intercepts, and do you see very clearly the 2 locations where we have slopes of 0? Yeah, and they're maxes and min locations, right? I mean, that's what we're looking at here. So we have 2 locations that we're referencing. That wasn't good. That's a little bit better. And, you know, if I curved this and went back down and crossed the x-axis again, I would have, because of the curving, another location where I actually have an intercept. Now, there is one thing to notice on this. This says, in both cases, and you wrote it in there, but let me highlight it, at least one. And this previous one said that too. I'm sorry, the next one said that too. At least n minus 1. It could have more. So let me just draw you a picture of how that would be the case, because you might be thinking, well, that doesn't make sense. So there's nothing that says that you actually have to cross the axis in order to have a turning point. So you could have a graph that does something like this, right? You see what I'm saying? I mean, it could even do like this in order to actually make it work with my definitions the way they're set up. So it has 2 x-intercepts, right? My theorem says I should have at least one location where it has a slope of 0, and this one actually has 3, doesn't it? Are you guys with me? So this is sort of the minimum, the bare minimum of what could possibly happen as a result. But there could be more things happening as a result as well. All right, so we're going to do an example for how this applies. It says prove the following. So please, as you are doing your homework, please reference back these 2 examples that we're about to do, because this is exactly how you do them. I know the word prove can be a little bit freaky because you have all sorts of images in your mind of what that might look like in terms of geometry proofs or trigonometry proving identities or things like that. This is the kind of proof that we're referring to here, okay? So it says prove that x to the 4th plus 6x squared minus 1 has exactly 2 solutions. Now, exactly is not what either of those theorems said. They said at least. So we're going to have to do something different to sort of cap this and say, and there's no more than something going on. So let me show you how we do this. Before we can do anything, just like in the last two examples, we have to confirm that this really has the conditions met. The conditions say that it should be continuous and differentiable. So we have to verify for sure that that really happens. So is this continuous? Is it differentiable? Yes. And what's the reason for both? Yes, because it's a polynomial. Yes?
So, what happens if we check and it's not?
The ones that you're working with are going to be differentiable and continuous, at least on the interval they give you when they're working. So you don't have to worry too much about it. But I do want you to confirm that you've actually considered that as a possibility, because that just is the ones that they're showing you right now in your textbook. If it didn't apply, generally speaking though, if it didn't apply, it would mean that the results may not actually be accurate. That's what it would actually mean. So, yeah. Okay, so the results should apply next, okay? All right, so we're going to start with a picture. We're going to look at a graph of this thing and kind of get a feel for what it sort of looks like. This is an x to the fourth graph. So take your calculator. And what I want you to do is I want you to put in the left-hand side of this into y1. So this is going to say y1 equals x to the fourth plus 6x squared minus 1. And you can just use a standard 10 by 10 window, or sorry, 20 by 20 window, but negative 10 to 10, negative 10 to 10 should be sufficient. So the standard window in your calculator. All right, so roughly speaking, what does the graph visually look like? It looks like a parabola. I mean, it isn't a parabola exactly, right? Why do you know it's not really a parabola? Because what? It's a power 4, right? It has an exponent with a power of 4. Quadratic equations, quadratic formulas only have power 2, right? That's their highest exponent. So this is not a parabola, but it has some very common features to a parabola. It has that opening up U shape, all right? It should feel like it's a little bit tighter than a parabola, right? A little narrower. So, but roughly speaking, your picture looks something like this, I think. Does that look like your picture, more or less? Okay. So it seems reasonable that this has how many solutions? What's it look like? 2. And by solutions, I mean x-intercepts, all right? So we're going to write that down just to jot a note to ourselves. I'm supposed to be proving that it has 2, but the very first thing that I should do when I'm proving it is convince myself that I think it's true. If I graph this thing and it crosses the axis 3 times, it's going to be really difficult for me to construct any logical proof in my mind about why this should only be crossing it twice. Are you guys with me? So what you just did not prove anything. It actually just gave you justification for why you would try to prove it. So this looks like it has 2 solutions. And by solutions, remember, we mean places where f of x equals 0. Okay, or x-intercepts is another way of saying that. All right. We need to show, though, that it really doesn't have any more than that. All right? At least 2 means that it has to have 2 and no more, and also have no fewer. All right? So we need to show 2 things. We need to show, number 1, that it doesn't have fewer. So where it doesn't have fewer than 2 solutions. And the second thing is that it doesn't have more than 2. Obviously, if it doesn't have fewer than 2 and it doesn't have more than 2, then it must have 2. So we're kind of doing this in a roundabout way, right? We're doing it sort of by process of elimination. So it doesn't have more than 2 solutions. All right, the doesn't have fewer than 2 solutions is going to come from something you have seen back in Chapter 1. Do you remember something called the intermediate value theorem? You had a question, a true-false question on your test about it. The most common thing that you were forgetting, some of you who got that wrong, was the idea of it being continuous, and you see that playing in play here again too, right, something being continuous. So what we're going to do is we're going to test 3 points. In particular, what we want to show is we want to show that there's some location up here that's above the x-axis, some location that's below the x-axis, and another location that's above the x-axis. Because if it's above the x-axis and it's below, it had to cross. Okay, so that's what we're going to do. So in general, you can pick pretty much any values to be on the outer edges. There's a really nice value to pick that's the in-between lower value. What might you pick? 0. Yeah, I like that one. So we're going to test 3 values. So we're going to test f of what? What do you want to test as your first leftmost value? X value.
-1.
I think that's not quite big enough.
-2.
-2 is. I'm cheating. Yes, I know. -2 is big enough. If you tested -1 and you got a negative, you know you would just test something else. So it's not really cheating. I'm just helping you, right?
Yeah.
And we're going to test f of 0, and then we're going to test f of 2. So these are my 3 test points. All right, so plug -2 into the equation and tell me what you get. 41? I have 39 written down. 39? Maybe there's a sign wrong. Did you do +1 in the end instead of -1 maybe? It's okay. What do you guys get for f of 0? That's -1. And how about f of 2? 39. Okay, so the fact that you have a positive value and then a negative value, and then a negative value and then a positive value means it crosses the x-axis. So by the intermediate value theorem, IVT, this graph has at least, that doesn't look like least because it's all run together. Let me try that again. 2 solutions. So it does not have fewer than 2. It has to have at least 2 solutions. That's what the intermediate value theorem is doing for us. Now we have to show that it doesn't have more than, because that was the other thought, right? It could potentially have more than 2 solutions. So why does it not have more than 2? Well, let's take a look. We're going to use the mean value theorem to do this one. Okay, and here's how we're going to do that. We're going to take the derivative. So somebody help me out. What is the derivative of my function?
4x cubed plus 6x.
Oops, I left my 4 out. 4x cubed plus 6x. Everyone agree? I don't think it's 6x.
Plus
12x maybe?
12x.
Yeah, that's okay. Yeah, 12x. And we're going to set it equal to 0, okay? So let's solve this. How do we solve this equation, 4x cubed plus 12x equals 0? Factor. We're going to factor out an x. We could even factor out a 4, couldn't we, Edgar? So I'll factor out a 4x, which would leave me with what? X squared. And then plus, what was it? 3. Good. All right, so if we try to solve this, 4x, that part equals 0 when? When x is 0. How about this one? When does x squared plus 3 equal 0? It would be the square root of -3, which would be a problem. You have a square root of a negative in the real number system, right? Think about it. This equation or this expression can't be 0 because this is something squared. That's a positive number plus another positive number. I can't get back to 0 in the real numbers. So this piece right here has no solution in the real number system. So there's only one value right here. Only one value right here where I have a slope of 0. That means there's only one maximum or only one minimum on the graph. So think back to this picture over here that we were drawing. If I have only one case where I have a horizontal line, could it cross the graph more than twice? Not possible. Not possible. That's what the mean value theorem says. The mean value theorem says that it can't have 3 solutions because I only have, if it had 3, it would have to have at least 2 of these crossing locations two of these horizontal tangent lines. And it doesn't have two horizontal tangent lines, it only has one. So this is telling us we have only one. I'll actually jot down a little bit of that. Do I have another space? I do. So we have only one horizontal tangent line. Hence, at most, two solutions to f of x equals 0. At most two, that's all I've got. So I have exactly two. And I numbered them, so I'll number them here by 1 and 2 above. In one place I said I have at most 2, in the other place I said I had at least 2, so it must be exactly 2. Can't have more than 2, can't have less than 2, it must be 2.
So if we were like answering this in the example, would our answer be the two, what's it called, where we put by IBT and scratch IBT, we put that as the answer? And then
Well, see, you have to remember that a proof is a justification. So the answer is all of everything we wrote.
okay, so,
I mean, the answer is, does it have exactly 2? Well, yes, but you knew that in the beginning because it told you. You're going to prove it has exactly 2. So the answer isn't really it has exactly 2. The answer is the justifications that show why it has exactly 2. And that's all of the work we did. All of it. It's a lot.
The part you just wrote, the last part,
Uh-huh. What about that?
is that like the,
That's the conclusion. It's like the last step in a geometry proof, and it says, well, by this piece and this piece, now I have the following. It's the concluding statement, like a conclusion of a paper or something like that.